tout le monde. Hello everybody. So welcome to this session of the mathematical physics seminar. And today it's our pleasure. Kirone from IPhT will talk about an exact solution of a macroscopic fluctuation.
Thank you, Jérémy and Vincent. I'm grateful to you for invitation, and I'm happy to speak in our lab at home. It's always a pleasure. So I'm going to tell you about macroscopic fluctuations in classical, non-quantum, interacting particle systems far from equilibrium. So of course it's a kind of technical title. I would have to define a few words. So to do that, I will recall you what we know about thermal fluctuations, macroscopic fluctuations at equilibrium. So this theory is quite old. If you consider a system at thermal equilibrium, in fact, Einstein already in 1906 has the idea that one could revert Boltzmann formula that gives you the number of microscopic states omega as a function of the entropy, and write that omega is the exponential of s over kb, and use this formula of Boltzmann-Einstein to compute how thermodynamic observables fluctuate around their average values. We know that thermodynamics gives relations between average variables. Entropy is maximized for a system in the microcanonical ensemble. But we can ask ourselves some questions about non-typical states, even at thermal equilibrium. For example, you can consider this piece of chalk, put it on the table, and compute using this formula the probability that spontaneously it goes up by 1 meter. It's a very, very small number. It's exponential minus 10 to the power 23, typically. But it's possible to compute that by inverting this Boltzmann formula. Of course, if you expand the entropy near equilibrium, its first derivatives are 0 because it's a maximal state. The second derivative are definite negative. The entropy is a convex function. And you automatically get a Gaussian distribution for thermodynamic observables fluctuating in the vicinity of equilibrium. In fact, what will play the role of the quadratic form if you do that is the second derivative of the entropy of the Hessian of the entropy. So that's typical, although it's not taught in many courses, but this is of course quite old, and this allows to construct the theory of macroscopic fluctuations at equilibrium. Equilibrium state is of course one very important property of equilibrium is that it's time reversal invariant. If you make a movie of a system at thermal equilibrium and project it backwards, nobody will be able to say that you did a mistake in projecting the movie. So that's the first point. Another thing is that suppose we take a simple box like that at thermal equilibrium, closed, with n particles, volume V, temperature T, so it has a typical density n over V. And we consider a small box here, which is again small but contains a very large number of particles, so it's kind of mesoscopic small box. And in small v, you have small n particles, and the temperature is T, and open. It's just a kind of imaginary volume. It's not a closed thing. And we compute the number of particles in that. So we have an empirical density, small n over small v. And again, if we make a plot of this empirical density, suppose we put a small detector here, and we're able to measure the density in this small volume. Of course, this empirical density will be fluctuating around ρ0, the average value, the typical value, but as a function of time, the empirical density will fluctuate. And one can be interested in the fluctuations. So if I now look at a static fluctuation at a given time t0, static fluctuations can be computed by using Einstein formula, as long as they are small. They are not large excursions. I remain in the vicinity of ρ0. I don't go to 2 ρ0 or ρ0 over 10. Just remain in that vicinity. But one may be interested also to look at how this time series, how this history, what is the probability of observing such a history, such a path. So we may be interested in static fluctuations or in dynamical fluctuations, which fluctuate with time. Okay? So it's a kind of more elaborate. Of course, if we know the probability of a path by taking everything at a given time, we can go back to the static fluctuations. So this was investigated by Onsager and Macroscopic. Onsager first, and then Onsager and Macroscopic in the 50s. So for small excursions, and they gave a formula that I'm going to show you in a second for a path integral that gives you the probability of each history in thermal equilibrium. Okay, so that's another thing I wanted to tell you. Another thing which is very, very important, if you look at, I'm at thermal equilibrium here, is that that's exactly what I said before, if you look at this history or look at the time reverse history, they are statistically identical. You will not be able to say that I do things backwards in time. In other words, if you have a here kind of positive fluctuation, if I make a kind of blow up of this part here, statistically, the curve going towards a positive fluctuation and the part of the curve which restores equilibrium, yeah, not possible to distinguish them. There's no difference between going upwards and going downwards at thermal equilibrium. Okay, so this is equilibrium, and to do a more complete theory, you need to invoke quite a few things, to do a complete theory at equilibrium. First of all, you have to express how things vary with time. So you have to express some dynamical law for variation for your system at equilibrium. And these dynamical laws are essentially phenomenological. They are essentially generalizations of Fourier's law that we all learned, that the current is minus lambda, the gradient of temperature. And Onsager built on that for more general phenomena. And he constructed a response matrix. So you impose to your system some constraints, some gradients. You put a difference of temperature, you put a difference of pressure, a difference of concentration, a difference of potential, and you have a current which develops, or a few currents that develop themselves into your system. And at the linear level, you can always write that the current you get are linearly related to the gradients you impose to your system. So Fourier's law is the most basic law in this kind of phenomenological description. More generally, you can see that the currents are L, a matrix L, Onsager matrix, times the gradients. Onsager proved in 31 that this matrix L is symmetrical, or antisymmetrical if you have some magnetic current or some rotations. So these are Onsager reciprocity relations, which are fundamentally based on time reversal invariance. And then, 20 years later, Onsager and Merkloop gave, as I told you, a path integral for these fluctuations at equilibrium, which is expressed by this formula. So the fluctuations of thermodynamic variables are given by a Gaussian integral. And this measure, in fact, is nothing but the measure associated to an Einstein-Uhlenbeck process of the type, a simple Langevin equation for a vector plus y plus. So if you write the path integral associated with this Langevin equation, you will get that one. And R is the Hessian of the entropy from Einstein point of view, and this is Onsager matrix that satisfies the reciprocity law. So all this long introduction about thermal equilibrium that most of us have seen in one way or the other is to show you that these kind of ideas can be generalized far from equilibrium. And in fact, the macroscopic fluctuation theory I'm going to talk about is really a generalization of this Onsager-Markov formula, but for systems which are not at equilibrium. So what do I mean by a system which is not at equilibrium? Well, suppose you connect your cube here, your room, to two reservoirs at two different densities, ρ plus and ρ minus. Then you will have a current going through your box, okay? The current always goes from high densities to low densities, so now time reversal invariance is broken. You cannot project your film backwards, you will see that something is going wrong. And the same question can be asked if you look at a small volume within your box, there will be an average value. The average value, you can always say, okay, it's the value given by Fourier's law, linear decrease typically between rho plus and rho minus, okay. But then you have also fluctuations. These fluctuations will not be time reversal invariant, so going out and coming back to stationarity are not symmetric by reversibility. How can you give a kind of path integral? How can you characterize the histories in such a system? So this would be the goal. Of course, we are not still there, but for some very specific systems, it's possible to construct a theory. And for even more simpler systems, typically in one dimension, it's possible to solve that theory and to get analytical results. So that's the goal of the talk today. So now let's go to systems which are far from equilibrium. And I will tell you about large deviations and MFT, macroscopic fluctuation theory. So let's redo the picture in 1D. If we have a bar of metal, whatever you like, a gas, which connects with two reservoirs at two different potentials or temperatures or chemical potentials or densities, at least at the hydrodynamic level, we can do a kind of description of this system. We can write a generalized Fourier equation and say, by using the conservation law, that the time derivative of a local density at point x at time t is minus the divergence of a current, and the current is given by minus the diffusion constant gradient of rho times an external field, which I call E or nu, times the conductivity. So that's a kind of phenomenological law. Again, for us physicists, we could write it without thinking about anything. The nice point is that for a large number of models, essentially in 1D, but there are generalizations, a whole bunch of mathematicians or mathematical physicists, starting from the 80s, have been able to prove rigorously that hydrodynamic limits exist, starting from some microscopic dynamics. And maybe the most famous name in this field is Raghuvaradan. We got the Abel Prize for this work. But there are many, many, many people who participated to this whole field of probability theory known as hydrodynamic limits. So a hydrodynamic equation, again for us, it's kind of very natural to write something like that. A hydrodynamic equation is really the equivalent in the sense of probabilities of a law of large numbers. It tells you how average values, local average values, local in time and space, evolve with time. So it's a law of large numbers, but as you can see, there are no fluctuations here involved. If I go to stationarity and I have a constant d, for example, again I will have a linear behavior of the density through my system. There is no noise here, there is no fluctuation, it's only at the level of average value. By the way, in this type of equations, you have the diffusion constant and the conductivity d and sigma that appear. These transport coefficients, they are data that you have to import from microscopic scale. You cannot get them from macroscopic considerations only. You have some formulas like the Kubo formula and so on, but you have to work out the microscopic dynamics to be able to put them into your hydrodynamic equations. Just as you know, viscosity in Euler or Navier-Stokes equations, the transport coefficients in hydrodynamics, you have to take them from empirics or from some other consideration, but they are not predicted by hydrodynamic itself. So how can you take fluctuations into account? So before I do that, I will give you some examples.
Oh, hang on. Sorry.
Yeah?
The reservoirs,
Yeah.
they are represented simply by
Boundary conditions.
density.
Yeah, let's see. Yeah. In this example.
Temperature or?
So it could be temperatures if you write a kind of heat equation here, for example. Temperature is so much entaché, so much connected with thermodynamics It's always difficult to say, why do you talk about temperature? You're out of equilibrium and so on. But you could do it also for temperature. Then you would talk about energy transport and forget about temperature and talk about energy flux and things like that. Temperature is always a bit tricky, like entropy. These words are so close to equilibrium.
Kirone, so,
Yeah.
sigma, you said it's a field?
So now sigma and d are functions, and this is the diffusion constant, and this is the conductivity. Conductivity, so the sigma that we learn, J is equal to sigma E. This part is really J is equal to sigma E that we learn in small classes. It's Ohm's law, if you want. Okay. So let's look at some examples. If you take, so typically these kind of ideas, but not only, they are applied to lattice gases, so simple models on lattices. So if we take on the lattice, it doesn't have to be 1D, but it's easier to draw. If you take random walkers, without any interaction, they can cross each other. D is 1, and sigma is 2 rho. Brownian motions, if you want. If you take the simple exclusion process, I'm going to talk a lot about, so now you have hardcore interaction, so you don't allow a site to be doubly occupied. So a particle cannot jump to a site which is already occupied. Then D is 1 and sigma is 2 rho, 1 minus rho. There is a model of heat and heat and energy transport, which is known as the Kipnis-Marquardt-Prisutti model, in which, so it's a model again on the lattice, but you don't have particles. You put a certain amount of energy, so it's a continuous variable, EI plus 1. And the dynamics is that at each time you select a site, you break the energy EI into two parts, EI1 and EI2, arbitrarily, and you give this energy to the two neighbors, and you evolve like that. G is 1, sigma is 2 rho square. So people have tried to compute from the microscopic dynamics for many different models the values of D and sigma, which are the only ones we need at macroscopic level. For example, Paul, a few years ago, defined a series of models. One of them is a model that he called the repulsion process, which is now quite successful. So it's an exclusion process. You again have hardcore exclusion, but you have an extra constraint. You're not allowed to increase the number of aggregates, the number of nearest neighbor pairs. For example, in the exclusion process, this jump would be perfectly allowed, but in the Paul's repulsion process, it's not allowed. And here you see G and sigma are less trivial, more complicated functions, rational functions. There is a very popular model. I'm not going to enter into the details. Yeah.
In this last model of Paul,
yeah,
it means that you have like long-range interactions.
No, you just make local jumps, but you're not allowed to increase, to reduce the number of gaps. You're not allowed to increase the number of neighboring pairs.
Okay.
So it's really local. Yeah. There's a model which is very popular since the 80s, known as KLS, Katz-Leibovich-Spohn. It's really built upon the Ising model in any dimension. Again, it's easier to write things in one dimension. Essentially a kind of Glauber or Kawasaki dynamics of spin flip, but with some asymmetry between left and right. So I just write very quickly the rates. I don't want to get into them. And now, if you want to, of course, if you flip a spin, it will depend on what happens on the neighbors. In fact, on the two neighbors around it, because you can change the number of domain walls. And you can see that now D and sigma are much more complicated objects, but they can be computed. So it's not only restricted to very simple models where you can get formulas for D and sigma. Sometimes it's not possible either to get close formulas for D and sigma.
What is H?
So what is H? H, j'ai oublié. You have to, oui, it's just a parametric description of chi of rho. You cannot even write a formula for chi of rho or sigma of rho. You have to eliminate a parameter between them. So if you are able to invert this relation and put it back here, you get chi of rho. Just to tell you that it can become, it's not trivial all the time. Anyway, once you know d and sigma, you have your hydrodynamic equations. Okay. But again, no fluctuations. And we are interested in fluctuations. Again, if I connect my bar to two reservoirs, I know that I will have typically, thinking of Fourier, for example, or Fick, or whatever, Poiseuille, I have typically a linear slope for my density between rho plus and rho minus, upper and lower density. I have a typical current, capital J, given by Ohm's law, if you want, typically. But there can be fluctuations. You can have a profile which is a red profile, which is not the linear profile. You can have local currents which are not given by the typical average current of Ohm. And what we really would like to have is really a path probability descriptions of observing locally at a given time some current J of xt and some density rho and xt connected by conservation. ddt of rho is minus diversion of J because we don't create or destroy particles in the bulk. And this probability distribution in some nice models, so here comes some hidden hypotheses, they assume a so-called large deviation form is that in fact you can write this probability distribution as the exponential of minus the size of the system times the functional, capital I of J and rho. And this functional contains, in fact, the information, the statistical information about your currents and your densities in your system. If you know this I of J and rho, then you could compute these path integrals. You could compute the probability of having a rare event of a very high density or a very low density. And this principle is not an overarching principle. All systems do not satisfy that. But systems which are called driven diffusive systems, so systems which are locally diffusive, where you scale time and space with a square relation. Time, space is the square root of time. Such systems with local interactions, many of them can be shown rigorously to satisfy this large deviation principle. And for others, we just suppose it's true and carry on calculations. So some people say, I don't know how much you should take it seriously, that this kind of postulate, which is a kind of purely mathematical writing, is a kind of Boltzmann formula far from equilibrium. I mean, it's purely formal. If you like, you can always write that. The question is, how can we compute I? If I give you a principle to compute I...
What do you mean? Sorry to interrupt, but I find the notation a little bit confusing. What you mean is probability of the whole function.
Yeah, it's a functional probability, indeed.
And it's funny. And L appears factoring I, because I is also a function of the function J of x and t and rho of x and t.
Yes. So you're perfectly true. You see all the details.
I'll show an example later.
I will show you an example. In fact, L will disappear. The reason I wanted to emphasize this L here, which usually is in fact inside.
Yeah, I would have put it in.
Is in fact, and it will go inside immediately. It's because in fact it's an integral from 0 to L. So I rescaled. And I wanted to put that for aficionados, mathematicians, because in the case of large deviations, these people love to have a large factor in front of, exponential minus 10 to the power 23 or 1 over epsilon. So they like to have this large factor in front of, but it will disappear immediately.
But you know a priori that it's L and not L square or...
So, yeah, that's an important thing. It depends on the system. It's very often L, but it could be square root of L. It depends on the local interactions. In the case I'm looking at, it's going to be L. Yeah, or square root of T, because L and time scale diffusively. But it's not always the case, indeed.
Kirone, that sigma means that the corrections are subdominant in L. The corrections to this formula are subdominant
in principle, you should have an plus 1 plus 1 over L plus 1 over L square. And this should be in principle computable. For example, for systems that you can solve exactly by better on that, you can go to the subdominant corrections. But already if you have that, you're happy. Already you have something. So the question is, how can you get information about I? And this is precisely what macroscopic fluctuation theory tells you. So you see Hubert that I embody the L inside of the action. So we want to write this probability of having the current and the density as exponential minus an action, S of MFT. And this action, that's what the people around Jona-Lasinio developed for the last 15 years and so. This action is given as a very simple functional of the local current and the local density. So that's a kind of postulate. You can prove it for very simple systems, but again, you should take it as a kind of ansatz, and this is called the MFT action. So this is a functional of these two functions, S, J, and rho, and if you plug it back into the large deviation formula for the probability distribution, this gives you the action of the path integral. Okay, I will just justify it to you where it comes from in a few seconds, but again, you could take it as an assumption to start with.
But that is the E in your black hole formula. And this
So,
is square divided by sigma.
It's a bit like
More or
that.
less.
It's a bit like adding a noise. You will see it immediately. So somehow, now that you have the path integral, so you know how to compute, or at least you have an ansatz to compute the probability of any history, you can do statistical mechanics on many observables and try to compute averages, fluctuations, cumulant generating functions. You know what to start with. The thing is now you have to, typically for a given problem, you have some dominant paths which will dominate your statistics, as is the case often in statistical mechanics. Dominant contributions have much higher probability to occur than other ones. So you have to compute these dominant paths and then determine them. And once you have them, you can compute things precisely. So you see the philosophy behind that. So I'm going to answer your question, Ricardo. Indeed. So the thing is that, again, it's a question of point of view. Apart from Jona-Lasinio, the other people in this group are mathematical physicists. So they like to write things in this way, which seems cleaner to many people. We, or I personally, prefer to say that indeed what happened is that you start from this hydrodynamic equation that I wrote a few minutes ago, this hydrodynamic equation, and essentially you turn it into an algebra equation by adding noise to it. If you do that and do, path integrals, once you have noise in an equation, you can write a path integrals, you will end up with the Roman action. It's called the Roman action because all these people are around Jona-Lasinio, who is in Rome, so you end up with the MFT action. Okay, so essentially, even if I forget about E, and I add phenomenologically some noise, white noise in space and time to my equation, to my hydrodynamic determinist equation, and I turned it into a stochastic process, then the Wiener measure associated to that is precisely the MFT. Why is it not satisfactory for mathematical physicists? Is that this kind of equations for them is not well defined. It's a bit like, in fact, it's even more complicated than the KPZ equation. It contains nonlinearity, multiplicative noise, and so on and so on. So people prefer not to write it. And in many, many cases for which absolutely exact results exist, it's easier to prove this directly rather than going through the stochastic equation. So that's why. But it's, to be frank, for me it's equivalent. But for mathematicians it's not. So if I write this action, and I'm not going to go backwards again, but you can see that close to equilibrium, and this was done by the Rome group, this action boils down to Onsager-Markloop classical 1953 path integral around equilibrium. So it's really a nonlinear generalization of the Onsager-Markloop history, path history near equilibrium. But this is valid far from equilibrium. I don't have at all to assume that ρ plus and ρ minus are close to each other. The current can be large, the fluxes can be high, This is supposed to be true, even very far from equilibrium. So now the goal is quite simple, because typically if I want to solve a given problem, I have to do several points in path integrals. I have to look at dominant parts and try to compute things with this dominant part. So what I have to do is to find is to solve the Euler-Lagrange equations associated with this variational problem.
So the boundary conditions for rho are
I'm coming to it. Yeah, for example, but I'm going to it. The boundary conditions are the difficult thing, and I'm going to be very specific. Indeed, this is very important, as you probably know too. But at least in the bulk, I just have to write Euler-Lagrange equation for this classical variational problem. And if I do that, I end up with two coupled nonlinear equations. So one will be for rho, and one will be for j. So this is Euler-Lagrange. But as you know, from Euler-Lagrange, we can go to Hamilton by making a Legendre transform. And for x and v, I can go to x and p and q. And this is very useful to do that. So typically, one introduces a variable h, which is the momentum, which is conjugate to the current, and one keeps the density rho as a first variable. And doing all this process, doing the variational calculus, Euler-Lagrange, getting the Euler-Lagrange equations, going from the j variable to the momentum h variable, and writing the Hamilton equations, you end up with this system of coupled equations for rho and h. So they are nonlinear. They are stiff. For example, the equation for h contains minus a Laplacian, minus d is positive, so minus the second derivative, so there is a danger of blowing up. But these equations have an Hamiltonian structure, and the Hamiltonian is given by this rather simple formula. So you can write that dt rho is minus the functional derivative of this Hamiltonian by h, capital H, and dth is minus, and so on. You can really write Hamilton equations. And again, the only relevant information for microscopic world is embodied in the transport coefficients d and sigma. So the advantage of this formulation is that you are back to classical physics, traditional physics, not classical necessarily in the sense of non-quantum, but traditional physics. To study a system far from equilibrium, you end up by solving two PDEs, coupled PDEs, nonlinear.
In this case, so sigma and d are
Yes.
fixed by microscopic dynamics. There is no feedback loop of scale fluctuation of sigma.
No. Of course, you could imagine more complicated models where they could have to be determined self-consistently, but in these simple models, they are given by the microscopic rules of your dynamics. So again, I emphasize the fact that you have to solve two PDEs directly at the macroscopic level. You don't have to solve the system microscopically. You just have to analyze some kind of generalized hydrodynamic equations, which also contain the fluctuations. Unfortunately, and I saw Hubert grinning, these equations are not so beautiful, but they will become more beautiful soon.
And in d of rho depends, of course, on x, but also on t?
Yeah, you're grinning. But, okay, in the simple case, d can be equal to 1, but sigma depends on rho, x, and t, clearly. So this was the status a few years ago. Again, ending up with PDEs is very reassuring, because we know PDEs. So people starting doing some perturbation theory on these PDEs, putting them into the computer, using WKB. I mean, you can analyze PDEs, nonlinear PDEs, looking at some, stability analysis of these PDEs around some stationary solutions, and so on and so on. So this was the status, but just to put into words Hubert's grinning, indeed, although we can a principle, get some information about non-equilibrium, there are many mathematical and numerical difficulties. In fact, these equations are stiff, they are not very well posed, they have some bizarre boundary conditions we are going to talk about. And in fact, the only case where time-dependent equations were solved till a few years ago was non-interacting case. But then you really need to go into that for non-interacting underworkers. At least you can ask some questions which are not so easy to solve from microscopic probability and solve them using these PDEs, but it was not so satisfactory. And there were no analytic time-dependent solution of these equations which were known for coupled interacting systems. The only non-exact results were finally obtained by doing better ansatz at the microscopic level. And it's a bit like a metaphor, as if you couldn't do anything on 5-4 theory, and the only thing you had to do was to solve the Ising model in 2D, in 3D, in 4D, and then get information about the exponents, but you could not do any analysis on 5-4 or continuous coarse-grained theory. So that was the status. And very recently, in fact, for such equations and closely related equations which appear in optimal control or optimal fluctuation path problems, some solutions were found by various groups, the group of Grajenbrink and Ledoussal, the group of Baruch Mierson in Jerusalem, and the group of Benichou, Grabs et al. In LPTMC Jussieu, and also by us, and this is what I'm going to tell you about.
A question.
Oui.
Why did you go to Hamiltonian formalism instead of sticking to Euler-Lagrange equation?
There are a few answers for that. One reason is that, as is the case even in classical physics, you get a pair of two first-order differential equation in time instead of a second-order differential equation. They are much more symmetric.
Okay.
And they are much more, there are transformations that we can do in these levels, canonical transformations typically, that are much more easier to understand in this formulation than in the Euler-Lagrange one.
Last question. So the both equations go forward in time?
Yes. Yes. But as you can see, the second equation has a minus Laplacian, so it has a risk of blowing up in finite time. And it does have a finite time blow up. This turns mathematicians ballistic, but we are not mathematicians. So now I want to tell you something about scattering and inverse scattering, something very general, which a priori looks uncorrelated to what I'm going to say, but of course I will put all these ingredients together in a few minutes. So we all studied Schrödinger equation with a potential. We all started our first TD by computing scattering for the second one, scattering by a square well in 1D. So what we do when we study Schrödinger equation with a potential, you suppose the potential goes to 0 at infinity, you send a plane wave, and you look how it's reflected and how it's transmitted. Okay, all did that. And if the potential is not symmetric, one should send a plane wave in one direction and look the scattering, or send it from right to left and look at the scattering on the other direction. So the idea is that if you're able to know how potential scatters completely all possible plane waves, you have a good information about your potential. Okay. You should also know the bound states, but this kind of potential has no bound states, for example, so you have only scattered states. And so the data, the information about scattering is embodied by reflection and transmission coefficients from the left and from the right. So according to the books, they are written as R bar, T bar. Here I will use some more standard notation in the subfield of inverse scattering. They are called A, B, A bar, and B bar. But they are essentially the reflection and the transmission coefficients through a potential. Okay, we are all familiar with that. So, indeed, these scattering amplitudes A bar, B bar encode information about the potential. And one important question, which was already raised in the 40s, 50s, 60s, is how can we reconstruct the underlying potential knowing the scattering data? I mean, this comes even from optics in the 19th century. How do you reconstruct the thing from an image? Inverse problem. And this can be done. This is called inverse scattering problem. In fact, there is a linear equation, a linear integral equation that involves the Fourier transforms of the reflection and the transmission coefficients, the Fourier transform of this A bar, B bar, and they can allow you to compute the potential from that information. And this is known as the GLM, Gelfand-Levitan-Marchenko equations. So these are two things. We studied all the first part, maybe less about the second part, but you are easily convinced that this is an interesting problem, and of course, problem of reconstructing an object to its image, its holography or whatever. Not in the sense of string theory, of course, but of course something natural. Now let's go to something different, slightly different for the moment. There is a very classical nonlinear hydrodynamic dispersive wave equation, which is known as the Korteweg-de Vries equation, first order in time. It contains a Burgers type transport U, nabla U, Euler-Lagrange type of equation. Okay, not Euler-Lagrange. I mean hydrodynamic equation. It's everywhere. It's U nabla U, and the third order derivative in U. Second order would be the Burgers equation. Here it has a third order, so it's dispersive waves. And suppose we want to solve it with an initial condition at time t equal to 0. So this is a nonlinear high order equation, and people were interested in it because it describes some waves in canals, arises as a normal form from real hydrodynamic problems. This equation has an Hamiltonian structure, and people discovered that it has solitons, so nice exact solutions, wave-like exact solutions that remain undispersed during time. And also this equation has many conserved quantities. Some simple ones, like the integral of u, but even some more complicated ones, and people were able to construct an infinite number of them. So now comes the miracle. In the 70s, physicists, nonlinear physicists and applied mathematicians found a scheme to solve that equation, to solve KdV. This is so-called classical integrability. And the scheme is quite miraculous, and I'm just going to describe it to you. It's known as the inverse scattering method, and it goes as follows. So you want to solve KdV with initial condition u x0, capital U of x. So what you do first is that you put your initial condition, capital U of x, as a potential in a Schrödinger equation. You put it as a potential, and you solve this Schrödinger equation, and you compute the scattering data associated with it. A priori, it has nothing to do with KdV. But you just take the initial condition of KdV and put it in Schrödinger and give it to your students to compute reflection and transmission coefficients. And I call it A0, B0, A bar 0, and B bar 0. You could also, you're not able to solve KdV for the moment, but you could also take the solution of KdV, the potential, the hoped solution u, x, and t, and put it in Schrödinger equation again. Okay, suppose I give you the solution, you put it in, but you don't have it, but you can at least abstractly put it in the Schrödinger equation and compute the possibly, and this Schrödinger equation has some scattering data, A bar, B bar, at time t. Is it clear? Yeah? You put the initial condition, you have some scattering data, you put the solution at a given time, you have also scattering data. But all this is abstract. You may not be able to do it, and you don't even know what is uxt. But now comes the total miracle, is that, in fact, because uxt satisfies the KdV equation, this implies that the coefficients A and A bar do not change with time, so they remain equal to their initial values, and the coefficient B and B bar are equal to the initial ones just by a phase, exponential k cubed t. So if you are able to compute the initial scattering data, which is given to you because initial condition is known, okay? So if you are able to compute A0, B0, A bar 0, and B bar 0, you know, only by using the information that uxt is the solution of KdV, you know the values of A bar, B bar at any time. But then, you should be able to reconstruct your solution of KdV from the scattering data at time t by using Gelfand, Leviton, Marchenko, by using inverse scattering, and by solving a linear problem. So somehow, you have broken your nonlinear problem into a linear equation, linear integral equation, which is sometimes, often, easier to solve. Is the procedure clear? Yeah. So it's a kind of miracle, yeah? And in fact, the people who studied that really showed that this is exactly the analogous of a nonlinear Fourier transform. Think about Fourier transform, that's exactly what you do when you solve the heat equation. you take the initial condition, or the Schrödinger equation. You take the initial condition, you decompose it, you analyze it into plane waves at time t equals 0. You evolve the plane waves like exponential minus 4dk squared t for the heat equation, or IET for the Schrödinger equation, and at a given time you recompose your plane waves or your eigenfunctions to reconstruct your wave function. So it's the same thing, and in fact it's mathematically precise. You can show that when the nonlinear term in KdV vanishes, all this procedure boils down to Fourier transform. So what you do, again, in this scheme, at t equal to 0, ux0 by direct scattering gives you the scattering data at time t equal to 0. The evolution of the scattering data, A bar, B bar, up to time t is trivial. A is constant and B is a pure phase. And then, by inverse scattering, you should be able to reconstruct, or to get information at least, about your solution of your KdV equation at time t. That's the procedure. By the way, I didn't tell, this is just for the general knowledge, but as you can see that A is invariant and B just turns with a pure phase. I told you that this is a Hamiltonian system KdV. In fact, A are nothing but the action variables of your KdV system, and B are the angle variables in the sense of classical mechanics, action angle variables. Any question about that? Is it okay? So now we put everything together in the remaining few minutes. I will explain to you rapidly how the macroscopic fluctuation equations for the symmetric exclusion process and some others can be solved by using this inverse scattering technique. So now let's be specific. I will give a very specific problem. There are some other problems that can be solved by the same technique, but let's take the simplest one. So I consider on the infinite line, lattice Z, the symmetric exclusion process, particles which are hopping in continuous time, and which can make symmetrically nearest neighbor jumps with probability dt to the left, dt to the right. Only jumps to an already occupied site are forbidden, so this is a hardcore exclusion. I start with a system with so-called two-sided Bernoulli initial conditions, which means that I occupy negative sites. Each site is occupied independently from the others with probability rho minus, and empty with probability 1 minus rho minus. And on the right, each site is occupied with a rho plus and empty with 1 minus rho plus. If rho plus and rho minus are different, for example, if rho minus is bigger than rho plus, it means that I am starting with an initial. Something bad has happened. 2000, and it's 500 the maximum. Wow. Okay. If you want to put your marks, don't hesitate. I go on. What? And the variable we are interested in. So you see, this is the classical equivalent of what people do in quantum system. They call a quench. So I just have two half systems. And density rho plus and rho minus.
It's a good solution.
It's a good solution. And I join them, and now there will be a current flowing it. So it's a one-dimensional analog of this kind of picture, of course. And there will be a current flowing through the system, and I want to count how many particles have flown through the origin, positively from left to right, minus negatively from right to left. So that's the total current that have flown through the system between time 0 and t. Okay. If you look in the continuous limit, you can compute this total current as the over density on the right, on the right half of your system at time t. So if you compute the integral of rho x capital T final time minus rho x 0 from 0 to infinity, this gives you the excess current, the flow of particles that flew from left to right. So we are interested in the statistics of this random variable qt. The probability distribution, or this is again probability cuisine. What's interesting also is to compute the average of the exponential of lambda qt, which is the characteristic function, which is the Laplace transform of the probability distribution of qt. And one can show, here it's totally rigorous, that in the long time limit, it behaves like an exponential of square root of t times mu of lambda. If you know this function mu of lambda, by taking some logs and making expansion with respect to lambda around lambda equal to 0, you're able to compute the average of qt, the average of its square, of its cube, the full cumulant of qt. So in fact, this function here is the so-called cumulant generating function of the random variable qt. Probably people doing field theory call it connected free energy or something. I mean, we always take exponential and logs to get some simple objects. But this has a very nice probabilistic meaning. So the goal is to compute this mu lambda, this generating function of the cumulants in the long time limit, and also to understand the history, not only to get a punctual static distribution, but also to understand if I want to get some non-typical current through my system, what profile and what momentum will generate such a fluctuation. So now if you try to think about what I told you before, we have the macroscopic fluctuation theory measure given to us by the Roman group, but what we have to do in the path integral is to multiply by this exponential lambda qt and to take averages. We have the measure of each path, but now we have to compute exponential lambda qt weighted by this measure. Okay? We know what's the occurrence of every path, and we have to compute the statistics of this object knowing the measure of each history. Is it more or less clear?
There be at least one term proportional to t. I mean, the more you weigh, the more charges are injected in the system from the left, no?
Yes. So the current will be proportional to t, indeed.
Is it subtracted in qt?
Yes, I subtract the average value, indeed. So another thing maybe that I didn't write quite cleanly, and thank you for your question. I will also consider mostly, but not only, the case where rho is constant. So there I have no average value, and so I don't have to subtract it, and the fluctuation will be only in square root of t.
No, current is proportional to root of t.
The current? Oh yes, sorry, yeah, of course, yeah.
Oh,
I was confused. Sorry, Hubert. I was impressed by your question. If you look at this, if you look at this profile, and you forget about everything, and you just look at average behavior, it's the heat equation. And the heat equation, the solution is just the R function. So you have a square root of t in. Yeah. Sorry. Merci, Paul. So now let's go to the precise equations. What we have to solve are these MFT equations for rho and h, and the boundary conditions are a bit bizarre. I'm not going to go into the details of how you can get these boundary conditions. The way to get them, again, is to write, at least formally, is to write this path integral with this measure, multiply it by lambda, exponential lambda qt, and do variational calculus on that. I'm just going to give you a kind of hand-waving understanding of what these boundary conditions reflect. So these boundary conditions reflect the fact that first of all, you have this initial step function. So this is encoded the second boundary condition. And the first boundary condition at final time really reflects the fact that your observable qt is given by this integral, which contains the density at rho xt. So you really need to know the density on the right-hand side. So essentially exponential lambda qt will be exponential lambda rho xt at final time. So this gives you a boundary condition when you do variational calculus of the type here. Oh yes, I can use my pointer that I never used of the type here. So all in all, it boils down to solving this set of nonlinear hydrodynamic equations with these boundary conditions. And once you can solve them, you can compute the typical current and even the cumulant generating function that went through your system by using the solutions of these equations that I call rho star and H star. So here comes the mathematical problem. How can you solve these equations? And as I told you, these equations were not solved, only the microscopic calculation was done in a special case by Derrida and Gershenfeld, and more recently, 2 years ago, by Tomohiro Sasamoto, Imamura, and myself, by using some heavy Bethe-Ansatz technique on the infinite line integrable probability. You could at least compute mu by using these techniques, but you had no idea on the history. You could only compute the mu. So in the
So in history, you have just one boundary condition 0, and then the other one fixes lambda.
And the other one, no, lambda is given.
No, lambda is fixed.
Lambda is given. So you have two boundary conditions for the two equations, first order in time. And thank you for the question. The difficulty here, it's not a Cauchy problem. You don't know both functions at initial time or at final time. It's a kind of mixed time boundary condition. And this is the source of the main difficulty, even numerical one. People could not really solve numerically these equations. They had to use an iterative scheme, which is approximate, and it was quite hard to get information on that. Okay, how much time do I have left?
5 minutes.
5 minutes? Yeah, it should be okay almost. So, almost.
If you want 10, let's give you
10 is perfect. So, the thing is, okay, these equations look quite ugly, but there's one special case you can think about, is the case of low density, in which case you can approximate sigma by 2 rho, and forget about the nonlinear 1 minus rho here. And this case, where you have very few particles, very rare particles, you can think of them as Brownian motions, which are constrained to reflect to each other, bouncing with Descartes laws. So this is, in the low density limit, what you get is a system of Brownian particles which just bounce like balls through reflection around each other. And in that case, the IPhT equations look like that. And there is a very nice transformation known as the Hopf-Kohl transformation, which is a canonical transformation of these equations, which essentially goes to exponential variables. When you see that, you immediately see that it's a kind of WKB thing. And once you do this transformation for u and v, you decouple these equations, and in variables u and v, you just get two heat equations, one which is directly propagating, and one which is contra-propagating. So you somehow decouple the model and get a free parabolic model that you can solve. So this was done already before. In fact, this was done by Derrida and Gershenfeld 10 or 12 years ago. But going to the nonlinear case, the symmetric exclusion case, remained a kind of a war. So then what happened is that roughly a year ago, and this is really the guesswork of Hiroki Moriya, which is doing his PhD in Japan with Tomohiro Sasamoto. There are some deep reasons. I may answer to some questions later about why and how, but there is a transformation which generalizes the Hopf-Kohl transformation. If you go to low density and eliminate the nonlinear terms, you can see that it really boils down to the previous one. And this nonlinear transformation of the variable rho and h allow you to rewrite the IPhT equations in a very nice and very symmetric way in terms of two nonlinear equations, coupled nonlinear equations for the variables u and v. So if I forget about the nonlinear terms, I get my two contra-propagating heat equations, one directly and one oppositely in time, but of course you have nonlinear terms. And the nice feature is that these two equations, which are very symmetric and now very beautiful, and which are perfectly equivalent to the initial IPhT equations here, these two equations are known for a long time to be exactly solvable. They are known as, they are in fact a real-time analogous of the nonlinear Schrödinger equation, and they are known as the AKNS, Ablogitz, Knopf, Newell, and Ségur equations. If I put an I here, and I take V equal to U star, these equations are nothing but exactly the nonlinear Schrödinger equation that describes the Bose-Einstein condensates, for example. Anyway, these equations, forget about NLS, they stand for themselves, and they can be solved exactly by inverse scattering. So now you can apply the machinery. And another very important feature that goes back, and in fact the crucial feature, is that these very ugly looking boundary conditions here become much nicer in these new variables. They boil down to two delta functions, one at initial time and one at final time. So now you end up with these AKNS equations with some variables and so on, with some non-local in time, but rather nice looking boundary conditions. And I may need a few more minutes. I want to, if you're okay with me, I want to tell you a bit how AKNS can be solved exactly. So how can we solve exactly the AKNS equations? These equations. So if you look at these equations, they are coupled and nonlinear. And you remember that to solve KdV, you needed Schrödinger equation. To solve AKNS, you need Dirac equation in 1 + 1 dimension. The idea is to consider a two spinor, psi1 and psi2, or a two vector, two components, psi1 and psi2, and to consider two equations, one in space and one in time for this vector psi. Okay? So psi evolves with respect to space by a linear system with a matrix U that depends on U and V, and it evolves in time, again, according to a linear evolution, with a matrix V, which involves a wave vector K and the functions U and V that we don't know, which are solution of AKNS. So this is a Dirac equation, and if I write these two equations here, a priori, you have a compatibility condition. The time derivative of the first equation must be equal to the space derivative of the second equation. I mean, you cannot write two equations like that without writing compatibility. And if you do the calculation by taking this linear system, you can just, by a simple calculation, see that the compatibility between these two equations is precisely given if U and V satisfy the AKNS system. So the AKNS system can be rewritten as the compatibility equations between two linear Dirac type scattering problems. Are you still with me? Yeah? So once you have this Dirac type scattering problem here, with potentials U and V, I just rewrite it here. But this is a rather simple equation, in fact. These are linear equations with these two unknown potentials, but these two unknown potentials are given by delta functions at the boundary times. And scattering by a delta potential, you know how to do it. So you can do it. Okay? It's even simpler than scattering by a square potential. So once you, for these delta potentials, you can calculate the scattering data A and B. You can really do it explicitly. Okay. So that's what we did. We computed the scattering data, I'm going a bit faster, in terms of the unknown functions U and V, and we were able to get explicit expressions of the scattering data in terms of the Fourier transforms of the functions U and V. This, again, this is a bit long, but this is elementary, because you are just doing scattering by delta potentials. And once you have this scattering calculation, scattering data in terms of U and V, you can use the fact that the evolution of the scattering data is very simple with time. As I just before told you, it was very simple in the case of the KdV equation. For the AKNS equation, it's the same thing. So, knowing these boundary conditions, you can now compute the profile at the final time. And having the profile at the final time, sorry to go fast through the details, you can get an explicit formula for the Fourier transform of the profile at the final time. So it's not the profile itself, it's a Fourier transform, but who cares? Okay? If you know the Fourier transform, you can at least plot it. So knowing the profile at the final time, you can deduce the value of the cumulant generating function. And you can also plot the evolution of this profile from the initial time and the final time, and have an idea of how dynamically a non-typical fluctuation, a non-typical current is generated through the system. So what I drew here, thanks to Hubert and Paul, was the typical evolution through the heat equation. But now suppose that I want to have a non-typical fluctuation of my current, a non-typical value of the current through my system. So I'm starting with these initial conditions, rho minus and rho plus, but I want to bring to 0 a current which is not a typical one. So what will happen is that to create a current which is non-typical, you will have to take advantage of the fact that you have fluctuations in the initial condition, and you will start with the initial condition which overshoots the density. So you have a kind of an extra bump of particles behind 0 and a kind of thing in front of it. So that's rho at x equals 0. And this will push a lot of particles through your initial site, and in the end, you will have a deflation. So you will have something like, which looks like that. You will have a dip below and an extra above it, because you have pushed many systems. So you can see it here, maybe more precisely. In the initial condition, okay, let's do it like that. You have an extra accumulation of particles behind the 0 site and a kind of depletion of particles, more holes in front of it. And after the evolution, many particles have been pushed through the system, so you have less particles behind and more in front of it. And you can also compute how the momentum which drives your particles through the system evolves through time. So, okay, sorry for being late and going a bit fast in the end, but the idea was that you can marry inverse scattering with macroscopic fluctuation theory to get exact solutions of your non-equilibrium dynamics, and not only non-equilibrium statics. At the microscopic scale, indeed, you can use many tricks, all of them based upon generalizations of the beta ansatz, but this is very technical and very fragile. As soon as you modify your system a little bit, it becomes non-integrable, and you cannot use these techniques anymore. At the coarse-grained levels, you end up with PDEs. So these PDEs are complicated to solve, but it so happens that for the systems that we are looking at, and quite a few others, you can use this idea of inverse scattering to solve them exactly and to derive exact results at the macroscopic scale. And our hope, but we are not the only ones that believe that, but some other groups too, Le Dussal, Mearson, Benichou, and Gratz et al., we believe that using inverse scattering, so classical integrability at the macroscopic level, could be quite useful to study and investigate systems out of equilibrium and understand large deviations and current fluctuations in these kind of models. Thank you very much.
Questions?
So, is there an example where KTV would be playing the role that AKNS plays here? Or you really need coupled equations? KTV would not be.
So yeah, I don't know yet. Now there's a kind of dictionary going on at the microscopic scale, microscopic first, you have many models, and we were talking about that with Vincent just half an hour ago, like the Toda-Chain, which is a model coming from quantum mechanics, I imagine, that can be translated into a stochastic interacting particle system. And you can use technology from the Toda-Chain to get some information about non-equilibrium. Of course, the exclusion process is nothing but the XXZ spin chain, just slightly twisted and so on, with boundary conditions which are non-diagonal, etc., etc. But in the bulk, it's XXZ. ZEP is nothing but XXX. So the better ansatz for ZEP is better ansatz, 1931. So there are many models now. Calogero-Söderland, for example, can also be viewed as macroscopically as an interacting particle process with some stochastic behavior. So your question is perfectly legitimate. There is a hope that many macroscopic coarse-grained PDEs could be reinterpreted with some bizarre boundary conditions, with some slight twist, as modeling macroscopically some non-equilibrium systems. Indeed. To answer precisely, I don't know about KEV. It could be the case.
Nearly the same question that we were. If you do some statistics on these exact results, do they all belong to the AKNS, so-called AKNS scheme, or do we go beyond? Like Toda, you say. You know, so, Japanese school.
Yeah. So the only
usually enumerated all integrable PDEs in some sense.
Yeah. So because it's just something which is beginning, I have no answer. In fact, the only here is written everything that is known up to now, and indeed what Dussal did. So and Mearson, and in fact the group of Benichou did not exactly do the things in the same way, and okay, it was slightly different. For the moment being, it's all into the AKNS scheme. But it doesn't mean it's the only case, of course. But we all ended up with AKNS because we were looking with related problems. AKNS or some generalization. AKNS or what is called d-AKNS, in which you add a derivative here. Yeah, I wanted to talk about that, but I will not. Here's AKNS. D-AKNS is where you add a dx here and a dx here. Derivative AKNS. So this also appears. The derivative, which is also integrable. Indeed.
Yeah. Is there a reason why the boundary conditions become so simple? Because the boundary conditions are external to the transformation, right?
Yes, you're right. So no, there is no reason. And in fact, what happened, and this was again a kind of good miracle by this transformation, we tried many transformations. The boundary conditions were not nice, and for this one. In fact, if anybody had found this transformation before, he or she would have solved the problem before. Dussal was trying hard, for example. He had some very nice transformations, but not that one.
The correct transformation is somehow the one not which simplifies the equations, but
no, the one who transforms. Yes, you have other transformations who simplify the equation and transform it into some DAKNS or some nice-looking equations, but they are awful. In fact, thank you for asking the question. One thing which was known for a long time, indeed, which goes back to Hubert's question, relation between exclusion process is XXZ, indeed. So even at the macroscopic level, there is a way to transform these equations into the classical Landau-Lifshitz equations, which is the equation for a classical spin. The Landau-Lifshitz equation for a classical spin is an equation that tells you that, so you have, let's say, a line. At each point, you have a spin of norm 1 in 3 dimensions. Okay? And the classical Landau-Lifshitz equation is a classical limit of the XXX model, which tells you something like this. Okay, so I don't call it SXX. So you have S, which is S1, S2, S3 on the sphere. The norm is 1, and so on. And this is the classical Landau-Lifshitz equation. And this is the classical limit of XXX. And indeed, it was known that you could transform the MFT equations, which are here, into that one by using some kind of a strange non-local change of variable. So it's possible to do that. But then the boundary conditions became more formal. So somehow the idea that because this is known, and it was studied by Fadeyev and Baktajan, this is known to be integrable, the feeling that MFT should be integrable was there for very long. But it was not possible to do it in practice.
But this it is equivalent to KNS.
Yes.
And
yes.
In fact, it's what?
Yes, it is equivalent to KNS. Yeah, this step was somehow missing. It is equivalent, in fact, to NLS through some transformations. They are very beautiful geometric transformations. As this spin, this classical spin, is on the sphere. Its evolution makes a curve on the sphere. The curve on the sphere is a curve embedded in the sphere, in the physical sphere. So it has a torsion and a curvature. And you can write an effective equation for the torsion and the curvature of that curve, and that equation is NLS. But the problem is that each time when you went from MFT to here, and from LLE, non-lipids, to NLS, each time the boundary conditions were completely spread out and very complicated. So the transformation that I just wrote you is just a direct jump by somehow mixing these two transformations. And the boundary conditions behave well. Yeah, this could have been done before, of course, as always. As often. Yeah. No, it's nothing really magical. I mean, yeah, and it's really true that this strange transformation is a composition of two rather well-known transformations.
Now you can make a fortune in the stock market, right?
Tell me how, you better love
predict
to.
large fluctuations, I think.
Buy an apartment in Paris with plenty of books.
The reservoirs will be like the Federal Central Bank. I'm sure you can. Just talk to Bouchot.
Because the new law is trying to do something like that.
Yeah, David is visiting us in a few days, so maybe it's, if you want to join the discussion,
No, I
you're more than welcome. You're already rich enough, Hubert.
I don't want money.
You mentioned that there was this equations integrable via inverse scattering, you know, that have infinitely many integrals and many of the most. And somehow you write, for instance, these integrals, you know, first you like KDV looks
nice.
reasonable, you know, and then, you know, like momentum and energy, and then kind of becomes more and more bizarre. But for instance, here, if you try to write those integrals in terms of this rho and h, you know, did you try?
Yes, we tried. In fact, it was my mistake. I was maybe too pedagogical and too elementary in the end, in the beginning, and there are plenty of details that I put under the carpet. When you do these transformations, which are kind of non-local and quite complicated, in fact, when you try to invert them, you have to fix some constants. You see, these transformations relate the derivatives with u and v, so there are some boundary constants to fix. And to fix them, we need to use some conserved quantities to get precise formulas in the end. So we need to write 3 conserved quantities, not only the trivial one, 2 trivials and 1 non-trivial to really fix to invert the transformation.
Okay. No more questions? Thanks again.